2025 A-Level Combined Mathematics Paper 1 Part B, question number 13, Part B. Part A of this same question was discussed in a previous video, link in the top right, and Part C of this question will be discussed in a future video. Part B has to do with complex numbers and Argand diagrams. In this particular question, we can see this question says, let the complex number w be equal to negative square root of 2 times 3 plus I divided by 1 plus 2i, and given that we are asked to show that the modulus of w, or the size of the complex number w, is equal to 2, and that the eigenvalue of w, or arg of w, is equal to 3 pi by 4, where the arg value of a complex number is equal to the angle between the real positive axis and that complex number taken in the anticlockwise direction. After that, it then gives another complex number z. It says z is element of the complex numbers, and let z be that such that the modulus of z is equal to 2, so the size of the complex number z is the same as the size of the complex number w, and the argand of z is equal to pi by 3. So given this, they then say, also let the points a and b be the points representing the complex numbers z and w respectively. So a represents z and b represents w on an Argand diagram. So we have an Argand diagram with a real axis, imaginary axis, and a and b represent z and w. Given this, we're then asked to show that AB squared, which is the distance between the points A and B squared, is equal to 8 plus 2 times the square root of 2 minus 2 times the square root of 6. Now given this, we're then asked to let C be the midpoint of the 2 points A and B. So the line AB, you take the midpoint of it and call that point C. And then using the triangle AOC, where O is the origin or the 0, 0 point, deduce that the sine squared of 5 pi by 24 is equal to 1/8 of 4 plus the square root of 2 minus the square root of 6. Now you will notice, if we just multiply the inside part by 2 and divide by 2 here, we can see we get 1/16 of 8 plus 2 root 2 minus 2 root 6, which is exactly AB squared. So we can see there's going to be some relation to AB and the sine of 5 pi by 24 squared. So now, let's start off by solving this question by first considering the first part, where we have w, and simplify w down to show that the modulus of w is equal to 2 and the arg of w is equal to 3 pi by 4. To do that, what we're going to do is first off rewrite w. So we're going to rewrite w in our answer sheet, which is going to make it easier for us to refer to it back. So w is equal to negative square root of 2 times 3 plus I divided by 1 plus 2i. Now the first thing we're going to do is to make the denominator a real number. In order to make the denominator a real number, in this case, what we can do is to multiply the denominator by the complex conjugate of 1 plus 2i, as in 1 minus 2i. That's going to make the denominator a real number. So in order to do that, we need to multiply the top and the bottom by that same number, which means that w is equal to negative square root of 2 times 3 plus I divided by 1 plus 2i, and then we're going to multiply the top and the bottom by the same number, which is going to be the complex conjugate of 1 plus 2i, which is 1 minus 2i. So 1 minus 2i. So we're going to multiply by 1 minus 2i and divide by 1 minus 2i. Now since 1 minus 2i is not 0, there's nothing wrong with this. If we do this, we can see on top we're going to get negative square root of 2 multiplied by the product of 3 plus I and 1 minus 2i, which is going to be 3 times 1, which is 3, I times 1, which is I, so plus I, 3 times negative 2i, which is going to be minus 6i, and finally I times minus 2i, which is going to be minus 2i squared, which is going to be plus 2. And then on the denominator, we're going to have this thing right here, which is going to be the difference of squares, which is going to be 1 squared minus 2 squared I squared. Now I squared is going to be equal to negative 1, so we're going to get 1 plus, actually we'll write it directly as it is, 1 minus 2i, this thing squared, so 1 squared, and 2i squared. Now simplifying this down, we can see on the top we're going to get minus the square root of 2 multiplied by, and this part here is going to be equal to 3 plus 2, which is 5, and then I minus 6i, which is minus 5i, so minus 5i, and this is going to be divided by 1 minus 2 squared I squared is going to be negative 1 times negative 1 is going to be positive 1, so we have 1 plus 2 squared, which is going to be 5, so divide by 5. Now if we simplify this down, we can see what we're going to get. We can divide the 5 out from here, which is going to leave us with 5 minus 5 divided by 5 minus 5 divided by 5i, which is going to be 1 minus I. So we have minus square root of 2 times 1 minus I, which is going to be, I'm going to write as square root of 2 times negative 1 plus I. Now finally, what I'm going to do is to multiply the top and the bottom by the square root of 2 in order to get 2 times negative 1 over square root of 2 plus 1 over square root of 2i. Now the reason I'm going to do this is that now we can convert this into an angular form. We can convert this into a sine of, cosine of a certain value, and we can convert this into a sine of a certain value times I, which is the standard form for a complex number. And that will give us that this right here is going to be the modulus of that complex number. Now if we do this, we know that 1 over square root of 2 is associated with pi by 4 sine and cosine values. So due to this, if we just take a look at the values here, the cosine of the angle needs to be negative 1 over square root of 2 and the sine of the angle needs to be 1 over square root of 2. Now since the cosine is negative, this cannot be pi by 4. So we need to go another extra pi by 2 radians forward in order to make this thing negative. So in order to do that, what we're going to do is to take pi by 4 and we're going to add pi by 2 to it. If we do that, we get 2 pi by 4 plus pi by 4, which is going to be 3 pi by 4, which is exactly what we had in the question, 3 pi by 4. Which means that if we convert this, this is going to be equal to 2 times the cosine of 3 pi by 4, which is equal to negative 1 over square root of 2, plus I times the sine of that same angle, 3 pi by 4, which is equal to 1 over square root of 2. So then we have the form r times cos theta plus I sin theta. Now from this we can see that therefore the modulus of w must be equal to this value at the front here, which is equal to 2, so it's equal to 2, and the arc of w, since this angle here is in between 0 and 2 pi, we can see the arc of w is equal to that angle, which is 3 pi by 4. Now for whatever reason, if we got this angle to be outside of the range of 0 to 2 pi, then what we would do is to either add or subtract 2 pi until we get it within the range of 0 to 2 pi. But in this case, we chose an angle that is in between 0 and 2 pi, so we can just write that the arc of w is equal to that angle. So there we go. These are the two answers that we wanted. The modulus of w is proven to be 2 from the fact that when we write it in this form, the value at the front is going to be the modulus of w, and similarly the angle in the sine and cosine, where we have cosine theta plus I sin theta format, is going to be the argand of that value. So in this case, we have modulus of w and arc of w. So we've solved the first part of the question. Now for the second part, it says that we have to let another number z, which is an element of the complex numbers, be such that the modulus of z is also equal to 2. So that means that this value z has the same exact size as w. Both of them have modulus of 2. But the arc value of z is not equal to 3 pi by 4, rather it's equal to pi by 3 or 60 degrees. So we have 135 degrees here and 60 degrees here. We are then asked to let a and b be the points representing complex numbers z and w respectively on an argand diagram, and then the first question we are asked after that is to show that ab squared is equal to all of this. Now, due to this, what we're going to have to do next is to draw out this argand diagram with z and w on them with the correct angles and such, and then we're going to have to use the argand diagram to solve this question. Now, it's not necessary to do this. You can of course do it purely algebraically, but since they're pushing us, like not exactly telling us to use an argand diagram, but they're pushing us towards using an argand diagram, it would be wise for us to do so. So let's go down and do that. So we're going to go down here. We've already found w, so let's also define z. So let's say let z be an element of the complex numbers and the modulus of z be equal to 2 and the arc of z be equal to, as I remember, it's pi by 3. So now, given this, let's also say let a represent z and b represent w on the following argand diagram. So we're going to draw an argand diagram, and we're going to label on this argand diagram the points A and B given the data that we know. So we're going to call this argand diagram, and we're going to draw the argand diagram real quick, and then we're going to label the points Z and W. So there we go. I've drawn an argand diagram, simple argand diagram. Here we have the origin. Here I've also drawn additionally a circle which has a radius of 2. Now you might be wondering why I've done this, and the reason for this is that since our value z has a module of 2 and our value w also has a modulus of 2. Both of them will be lying on this circle centered at the origin with a radius of 2. And the reason for that, of course, is that the modulus is basically the distance of a complex number from the origin. So due to that, z is going to be somewhere on this circle and w is also going to be somewhere on this circle. Now if we consider the z's eigenvalue is pi by 3, meaning that going anti-clockwise from the real axis, the positive real axis, when we go like this, we're going to get z at a point where if we take the angle from the positive real axis in the anti-clockwise direction to that point, it's going to be pi by 3. So therefore, if we draw a line that has an angle of pi by 3 relative to the positive real axis in the anti-clockwise direction like this, so we can label this angle in this direction with an arrow like this to indicate we are turning in the anti-clockwise direction, and we label this angle as pi by 3. Now we know that z must be somewhere on this line. Now additionally to that, since we know that z is also on this circle, since the modulus of z is equal to 2, we can say that this point right here, the intersection of these two, must be z. So therefore this point here is the point A, which is representing the complex number z. Now using a similar logic, if we go up here, w's modulus is also equal to 2, meaning that w is on the circle. Furthermore, since the eigenvalue of w is equal to 3 pi by 4, the point w must be on a line that has an angle of 3 pi by 4 from the positive real axis in the anti-clockwise direction. So if we draw a line like this, it's something like this, not exactly, it has to be a little bit higher actually, since the angle here is 45 degrees. So if we mark that out, this angle here would be pi by 4. This angle of course is equal to pi by 2. So the sum of the two is going to be pi by 4 plus pi by 2, which is 3 pi by 4, which is the angle of this line. So therefore, this line has to be a line that is containing the point which is corresponding to w. Now, since the point w is also on the circle with a radius 2, we can say that the point w must be this point right here, which is the intersection of the line and the circle. So therefore, this point is the point B, which represents the complex number w. So there we go. We've drawn the point A and the point B on an Argand diagram. Now if we consider AB is this line right here. Now, if we consider the vector nature of complex numbers, we can see if this point, if this line here is representing w and this line here is representing z, then we have this line, and this line, which we can apply the triangle rule to and say that this vector here, w must be equal to the vector corresponding to AB. So AB complex number, we'll just call it like with a vector symbol like this, plus this line here, which is corresponding to the complex number z. So we have plus z, which means that the AB directional complex number must be equivalent to w minus z. Now if that's the case, then that means that the length AB is equal to the modulus of w minus z. Now with this, we can now find AB squared. We can find AB squared because if we square both sides, we can see that AB squared is equal to the modulus of z minus w squared. So we can write modulus of w minus z squared, which is the same exact thing as z minus w squared, since the modulus just cares about the length. It doesn't matter which order you put the two numbers in. So this is going to be the value of AB squared. Now, if we consider the modulus z minus w, in order to find it, we first need to consider w minus z. So w minus z is going to be the complex value corresponding to w, which as we can see here is equal to this, which I'm going to write as square root of 2 times negative 1 plus I. So we can see w is equal to square root of 2 times negative 1 plus I minus the value of z, which is, based on our values here, going to be equal to the modulus of z, which is 2 multiplied by cosine of theta, which is cosine of pi by 3, plus I times sine of theta, which is going to be the sine of pi by 3. So therefore, we have 2 times cosine of pi by 3 plus I sine of pi by 3, which is going to be equal to the square root of negative square root of 2 plus the square root of 2i, and then minus 2 times cosine of pi by 3, which is going to be equal to half. So we have half times 1, so minus 1, and then this bit right here, which is going to be sine of pi by 3 square root of 3 over 2. So the square root of 3 over 2 times 2, which is going to be minus square root of 3i. So this is our value. If we simplify down the real parts and imaginary parts separately, we can see we get minus 1 plus, actually we'll do it like this. We'll put a bracket with the minus on the outside, minus 1 plus square root of 2 for the real part, and then we have root 2 minus root 3 for the imaginary part. So we have plus root 2 minus root 3, or we could write minus root 3 minus root 2. It's all right. We can just write it like this, times I. So this is going to be the complex number that we have. So therefore, if we consider the modulus of w minus z, it's going to be the real part squared, square rooted, which is going to be the square root of 1 plus root 2 squared, 1 plus root 2 squared, plus the second part, which is going to be this thing squared. So we have root 2 minus root 3 squared. So therefore, if we consider AB squared is going to be equal to 1 plus square root of 2 squared plus root 2 minus root 3 squared. Going to the next page, if we simplify this down, we can see on the next page, if we write AB squared, it's going to be equal to this thing squared, which is going to be 1 squared, which is 1, plus 2 times 1 times square root of 2, which is going to be 2 root 2, plus the square root of 2 squared, which is going to be 2, so plus 2, and then this bit right here, which is going to be 2 root 2 squared, which is going to be plus 2. We're going to have 2 times root 2 times minus root 3, which is going to be minus 2 root 6. And finally, we're going to have root 3 minus root 3 squared, which is going to be root 3 times root 3, which is going to be 3, so plus 3. Simplifying this down, we can see that AB squared is equal to 1 plus 2, which is going to be 5, plus 3, which is going to be 8, plus 2 times the square root of 2, minus 2 times the square root of 6, so minus 2 root 6. And that's our answer. And we can see up here, that is the exact answer that we're supposed to get. We're supposed to get that AB squared is equal to 8 plus 2 root 2 minus 2 root 6. So now, for the final part, we're then asked to let C be the midpoint of AB, and then using the triangle AOC, which is a hint for us, where the O is the origin, deduce that this whole thing, the sine squared of 5 pi by 24, is equal to all of this. Now in order to do this, what we're going to do is to consider this Argand diagram. We could either redraw it, but I think it's alright to simply just draw on the same diagram. So if we draw on the same diagram, the point C is going to be the midpoint of AB, so it's going to be somewhere over here. Now, since this triangle here is isosceles, since this length is equal to this length, which is equal to 2, we can say that if we draw a line from this point, which is O, up to C, this angle here, OCA, is going to be 90 degrees. Furthermore, since this triangle is isosceles, this angle here, which I'm going to call theta, is going to be equal to this other angle here, which is also going to be theta. So you can say in writing, which we're going to do down there, since OB is equal to OA is equal to 2 also, we can say, since that's the case, if we consider the midpoint of AB and call it C, then COB is going to be equal to COA, which I'm going to call theta. And furthermore, we can also say that ACO or OCA is going to be equal to 90 degrees. So if we go down, if C is the midpoint, or instead of if, we could say let C be the midpoint. That's a little bit more forcing, so we'll say let C be the midpoint of AB, and then we can say since OA is equal to OB, which is equal to 2, we can say that first off, the angles COB is equal to the angle COA, which is equal to theta. I'm going to call it theta. And furthermore, we can say the angle OCA, we could say OCB as well. We'll actually say that. We say OCB are both equal to 90 degrees or pi by 2 radians. So given this, we can now see that if we consider the total angle BOA or AOB, therefore AOB, the angle AOB, which is equal to the sum of the angles COB plus COA. From the diagram, of course, you can see this. This is going to be equal to theta plus theta, which is going to be equal to 2 theta. So now, if we consider the angle AOB, the angle AOB here, this angle is the difference of this angle and this angle. So we can say that AOB is equal to the difference of this angle, which is the eigenvalue of B or the eigenvalue of W, and then minus this other eigenvalue, which is the eigenvalue of Z. So we can go down here and we can say additionally to this, we could call this, let's say, point number 1. We could also say AOB, the angle AOB, is equal to arg W minus arg Z, and we could also say like something like from diagram or something. From diagram, we know it's the case. So therefore, this angle AOB is equal to the arg of W, which is equal to 3 pi by 4, minus the arg of Z, which is equal to pi by 3. Now if we simplify this down, we can see for a common base, we're going to need 12 here. So if we say divide by 12, we're going to need to multiply this by 3, which gives us 9 pi. We're going to need to multiply this by 4, which gives us 4 pi, which means that the angle here is equal to 5 pi by 12, which is going to be fact number 2. Now from 1 and 2 we can see, this value here is 2 theta. It is also equal to 5 pi by 12, which means that theta is equal to 5 pi by 12 divided by 2, or 5 pi by 24. Now this is what's important for our question. Since the angle, the arg value of 5 pi by 24 is what we need, this angle is what we need in our question in order to find the sine of 5 pi by 12 and conclude that the sine squared of 5 pi by 12 is equal to all of this. So now, let's finally see where all of this links up. So if this angle here theta is equal to 5 pi by 24, and if we consider the sine value of this angle, it is going to be equal to the opposite side, which is going to be this side, AC, divided by the hypotenuse, which in this case is OA. So from this we can see, if we go down, we can see that the sine of 5 pi by 24, which is equal to the sine of theta, since theta is equal to 5 pi by 24, is equal to the side length AC divided by the side length OA. Now we know OA already. We know OA, since OA is equal to 2, since that value OA is equal to the eigenvalue of Z, which as we, not eigenvalue, is equal to modulus of Z, which as we found earlier is equal to 2. What we don't know is AC. But since C is the midpoint of AB, we know that this length is equal to this length. So double that length is equal to AB, meaning that AC is equal to AB over 2. So we can say here is equal to AB over 2 over OA, or AB over 2 OA. So now finally, we can substitute both of these values. We previously found AB squared, and we previously found, we defined OA based on the modulus of Z. So now, if we substitute the two values in and first square the thing and then substitute, we can see what we're going to get. For the sine squared, we can say like, therefore sine squared of 5 pi by 24 is going to be equal to this value, AB squared divided by the denominator squared, which is going to be 4 OA squared. So 4 OA squared. Now substituting the values in, AB squared we found earlier is equal to, AB squared is equal to 8 plus 2 root 2 minus 2 root 6. So substituting that in, we have 8 plus 2 root 2 minus 2 root 6. And as for the denominator, we have on the bottom 4 multiplied by OA squared, which is equal to 2, so 2 squared. Now if we simplify this down, we can see we have a 16 on the denominator, but on the numerator, we have a factorizable 2. There's a 2 in this, there's a 2 in this, and there's a 2 in this. So therefore, if we take just a 1/8 out, what we're left with is going to be all of this divided by 2, which is going to be 4, plus 2 root 2 divided by 2, which is going to be root 2, minus 2 root 2 divided by 2, which is going to be minus 2 root 6 divided by 2, which is going to be minus root 6. And there is our answer. We've proven that the sine squared of 5 pi by 24 is equal to 1/8 times 4 plus root 2 minus root 6. So that's going to be the end of our question. That's all the questions that we have in this simple complex number question. Now finally, if we consider the marks given for this question, at the start when you write w like this and then you multiply w by the complex conjugate and divide by the same complex conjugate of the denominator like this, you get 5 marks. When you then simplify that down and get to some point like this or a point like this, you get another 5 marks. When you then take this thing right here and you realize in order to get trigonometric values you're going to need to multiply and divide by the square root of 2 and get to this point right here, you get another 5 marks. When you then substitute in those two trigonometric values of this thing being equal to cosine of 3 pi by 4 and this being equal to the sine of 3 pi by 4, you get another 5 marks. And finally, when you conclude the modulus of w and the arg of w, you get another 5 marks. Now in the next part, when you consider z and w and you consider their argon diagram, when you conclude that this is going to be the case, it's going to be something like this, where ab squared is equal to the modulus of z minus w squared, you're going to get 5 marks. Then, when you substitute in the trigonometric values corresponding to z like this, you're going to get 5 marks. Now, in the actual mark scheme, what they've done is they've solved this separately, but I don't feel that that's necessary. You could just directly substitute if you want. But anyway, substituting the trigonometric values in the modulus and writing z in this form, you get 5 marks. When you then simplify that down and you get to 1 plus the square root of 3 times I, as in this part right here, you get 5 marks. When you simplify down further and you get that the modulus of w minus z is equal to all of this, meaning that ab squared is equal to this thing, you get 5 marks. And finally, when you simplify that down to get that ab squared is equal to the answer that they gave in the question, which is 8 plus 2 root 2 minus 2 root 6 like this, you get another 5 marks. Now, for the final part, when you do all of this trigonometric stuff right here, when you finally get this bit where you realize that the angle AOB is equal to arc W minus arc Z, which you get to simplify down to 5 pi by 12 and conclude that the angle theta therefore must be equal to 5 pi by 24, you get 5 marks. So you need to establish the geometric connection between the value 5 pi by 24 and the actual eigenvalues of the two complex numbers Z and W and their relationship with the diagram. Once you do that, when you then write down either sine of 5 pi by 24 in terms of A, B and OA like this, or you write it square down like this as this bit right here, you get 5 marks. When you then substitute the values and simplify down to the final answer, you get another 5 marks. So that's going to be all for this video. I hope you enjoyed. If you have any feedback, post in the comments down below. Thank you for watching and goodbye.